DuckDuckGo Control Alt Enter Windows say text s privacy. Exiting narrator.
Good evening, and welcome to Average Expectations. It is once again the problem set due date night, so I expect to be interrupted more than once to answer questions. We'll see how that goes. Now, it's been 2 weeks since I was working on projects, and that's because it was just getting pretty busy. In fact, I'm going to change things so that we're streaming every other week. Okay, that's easy enough. And I guess I have to change it on my channel too. About... You know what, I'll just leave it on the channel. It's not like this really matters. Now, last time we were... Let's see, where was I? I was working on the singing piano project. So, what's going on with this project? Let's see. Last time, I remember I talked about some Fourier synthesis stuff, and then we talked about actually building a synthesizer. I copied some code, as I remember. I don't know if I got all of this done. Actually, I think I got most of it done. So we have a notebook. We've got some sound. We've got a loss function. We can even visualize differences. and I haven't done that last part. Okay, so basically, today I'm just going to keep working on this project in order to actually create. Basically, the goal is we're going to use a piano to approximate the sounds of other instruments. And in order to do this, we need to kind of cobble together a piano sound and test how different that is with these other instruments. And we're doing all of this in that frequency space, so in spectrograms. And so what we need is a kind of to be able to play arbitrary notes on our virtual piano and figure out what that spectrogram looks like, and that way we can compare it with our target. So today we're going to try fixing up the transposition part of this and also getting the other part working, which is to be able to combine multiple notes together in order to get chords. So I'm going to flip over to the code here. Okay, yeah, so I kind of remember what's going on here. What I was working on is, let's see, I copied all this code over. That was from the previous person's code. So this was the GitHub that was already doing this. And what I need to do is basically be able to, this was just some testing, right? And I think I was doing some transpositions here, yes. So I have a function currently to transpose notes around, because I need two things to be able to generate arbitrary piano noises. I need to be able to take some sample, which is basically just a quick recording of a piano playing, and I need to take this sample and move it around to wherever I actually am playing the notes, and that's what the transposition part does. The other thing I need is to combine the sounds, and I didn't do this last time. I was kind of stuck on the transposition part. And also, the other problem with the transposing part was that last time I did this, it wasn't sounding very good. And if I recall correctly, that's because when I transposed notes, they kind of ended up, how to describe it? It's like I was moving things into new bins. But the problem with those bins was that they didn't line up perfectly. So then you ended up getting some gaps between bins because you were copying like maybe slightly off to like a bin a little higher or lower than it should be. And then you would get like double ups where two notes map to the same bin, or you skip a bin in the middle. Yeah, and that created some weird kind of effects, like filter effects. So I'm gonna try to fix that today. I have an idea for how to fix that, but I don't know if it's the best way. I was thinking of doing linear interpolation, so maybe I should go over the goal today first. So step one. Transposition. So what we have is some samples. So the thing is, while in principle I could get a sample for every note of the piano, and in fact maybe that's like the easier way to do this, to cheat this, is just to have samples of every instrument. I would like the flexibility, however, to be able to like just transpose things around, and this is because let's say I only have a few samples of some source instrument. Maybe it's not a piano, maybe I end up picking a different instrument as my source to synthesize from. In that case, I actually would need to be able to generate all the notes that instrument can possibly play, even if I don't have access to the instrument. And in that case, it would basically, you can fake that by transposing the sample you have to the notes you don't have. Okay, we want any pitch. So, what's the problem? Currently, you can think of it as I have, let's say I've got a frequency bin here, right? So remember, the spectrogram's like chopping up the kind of the sound that you have into different frequencies. And so each bin, let's say this is like from 300 to 320 hertz or something, right? The problem is when we transpose it, right, it moves up to somewhere, let's say to here. And I'll draw an arrow. And when you transpose like that, well, maybe turns out your original bins look like this. And when you transpose it over, it kind of doesn't line up quite right. Right, so basically, let's say this is the bin that has some noise in it. And when it's moved up, it ends up here. And it's kind of in between these two existing frequency bins we have. So yeah, the bins are given to us by the Fourier transform that I'm running. So we can't really change where those bins go. And so what you end up with is you have noise or sound in this frequency band, but it needs to like really be in between the bins we have. And right now, my algorithm's just picking the closest bin and assigning the noise to that. So it's just going here. But the problem is, let's say you have two of these now. Let's say, let's say both of these have some noise in them. So I'm just going to color this a slightly different color. So now we're moving these two bins to here, and the nearest bin, let's say, just so happens to have like, let's say this bin goes here and this bin goes here. Well, then you're going to have a gap in between where you didn't have a gap before, right? Before, these two bins are side by side, and now you have two bins like this. Or conversely, suppose that the nearest bin is like here for both of them, right? In that case, if you bring both of these to this bin, right, then now you've kind of created a narrower frequency band than you had before, where these bins took up more space than you have here. So you can see both things happening will kind of change the profile of the sound a little bit, the frequency spectra. So obviously that's going to affect the quality of your results. And if I actually play back what we had last time, I think it's pretty obvious that there's some issues. Oops. So I remember generating these. So I believe this, let's see, I have playback on which ones? This is the original, and then I transpose it and I play that back instead, right? So it's easy enough. I'm just gonna run everything above. So it'll take a moment to connect to the Python kernel, I think. Yeah. Okay, and now I can generate the sounds. Okay, so here's my original, just the middle C. And then when I transpose it using my nearest bin, nearest frequency bin approach, it's gonna have some artifacts, I believe. Yeah, you can definitely hear that. Actually, you know, that's a little weird. Now that I think about it, like, that sounds even weirder than I remember it being. Huh. How far did I transpose C? By 0.9. Let's try it like 7.5. Okay, that's the original. Okay, that's even weirder than I remember. Huh. Okay, well, hopefully we can fix that. It clearly sounds off. And I think it's because of this. In fact, let's try plotting these. So I can plot these Fourier transform spectrograms. So let's just do that. Although I can't use this code directly because it loads it from file. So we actually want plot spec. Okay, cool. Let's try that. So here's my transpose notes. I have C4 and G3, and I think I can just plot spec on C4 and G3. And we'll take a look and compare what's going on between these two. Okay, so that's my C4, middle C. You can see the first spectrum peak is at 256 hertz. Yeah, roughly. That's, I think it's actually like 262 or something. But here is the one that's been transposed. Honestly, it doesn't look that different. So I'm kind of surprised that it sounds so off. Huh. Yeah, so you can tell it's been transposed because the first peak frequency is lower now. It's no longer at 256. That is a little surprising, to be honest, because I don't remember it sounding like this last time. Mind you, that was 2 weeks ago, so, I mean, obviously, maybe my memory is not as infallible as I think. Here's a different one. This is a higher pitch. Yeah, that sounds totally off. There's some weird stuff happening up in the high frequencies. Okay, so that's what we're gonna fix. Actually, I'm just gonna answer a real quick question about the assignment. Okay, there we go. No. Okay, so that's the problem. Here's my proposed solution. We are going to do linear interpolation, and if all else fails, I'll just write a script to like generate every single sample that we need from like something else, from a existing synthesizer. Like, so I've got MuseScore, for example, which is one of those music notation programs. And one of the things it does is it's got a built-in synthesizer. So I could just generate every single note. I'll just copy out the chromatic scale a couple times and then like generate some notes, and then I'll import that audio into Python and chop it up based on where the zeros are. Yeah, so that might be the backup plan for generating all the samples I need. But for now, I'm going to try linear interpolation because I've been thinking about this solution and it doesn't seem too hard to program in. So the idea is, instead of assigning each frequency so instead of like picking one bin for each current bin to get transposed to, we're going to weight up the kind of split up the bin among the closest two. And we're going to also not split this up evenly, but we're going to kind of weight the split according to how close. So there's a kind of generalization of this, which is basically a kernel. The idea is that in signal processing, you have some kind of weighting function, and we call that a kernel, right? And it could look like this, typically. Typically, it kind of looks like a normal curve. So let's see if I can draw a normal curve here. Yeah, so basically, you can imagine that instead of just dumping all your signal into one bin when you move it around, you actually kind of imagine that your true signal is a bump like this. And so if you want to move it around, right, it's gonna end up like here or something. So in the original, because computers are digital and not analog, right, it doesn't represent the signal as a smooth thing. It represents it as a bunch of discrete bits, just like in the frequency case, right? Here, I have some frequency bins. So you can think of that as trying to approximate this continuous signal like this, right? So basically, the problem we're facing is that when you move it over, like to here, right, these bins are going to be in different places. And so what we want is to kind of recover the proper size of these bins based on this kind of continuous thing. And we could do that using this kind of kernel function. Now, I don't want to get that fancy. So instead, I'm going to do kind of the simplest next best thing, which is to approximate this kind of approach using just a linear interpolation between the two nearest bins. So here's kind of the kernel view, right? So in fact, I'll copy this. The real signal frequency distribution, let's say, is a smooth curve. So this is an approximation that we have in the computer, right? And the linear approach, the linear interpolation, is we're just going to use the two nearest bins. So in the original, let's say our frequency is here, and we're moving it, let's say, to here, right? So the idea is that if it's here, what's the easiest way to draw this? Maybe using a different color. Yeah, like this. Okay, so the idea being that you... actually, you know what? Let's just do it this way. So previously, you have a bin which is like the full height of this curve in the middle. And now it's kind of, the curve's kind of in between two bins, like this, right? So what you do is you kind of average it out between these two bins. So they kind of look similar to the peak of this previous one. So what this looks like in practice is that it's just going to be the sum. These two bars here are going to add up to equal this one. And the amount you assign to each one will depend on how close you are to that one. So that kind of looks like this. I got to change the shape of this now. Because in linear interpolation, those the kind of shape you're dealing with is straight. So polyline. Yeah. So now we have something more like this. Not 3 lines, 2 lines. Up, down. Yeah, there we go. Yeah. So here's our source signal, right? And then here's where we're going. And basically, if you imagine that this peak lands right underneath one of these bins, then you have the same thing. There's no issue. But if it lands anywhere in between, you're going to rescale the bins based on where they kind of fall on this. So I'm just going to widen up these. Oops. Let's widen all of them together. Oh, I hear some cat fighting outside. So the neighbors have some cats around that are walking outdoors, and recently they've been making a lot of noise, which is really distressing to our cats. Apparently, they don't like it when other cats fight. So yeah, so this is the picture I wanted. Yeah, so you can see if the bin's right in the middle, you just give it all the energy. But if it's kind of on the side, you change it up based on how far off the center it is. Okay, cool. So that's the picture. Let's actually do some programming now. And I'll just check to see if there's any other questions. Nope. Excellent. All right. Okay, so here's our current transposition function. It says remove first bin because it's at 0 hertz. So there's an empty bin at the bottom. We have to get where we're going. So this is ideally where the midpoint of each bin goes. And then for each one of those, we have to find the closest available bin. So currently, this is finding the nearest bin. And what we want instead... Sorry, I'm hearing the cats again. It's a little distressing. I'm just gonna close the window so they don't hear that anymore. I'll be right back. Okay, so I'm back. Let's see. So currently, we're finding the nearest bin and dumping all of the energy in that frequency into that bin. And this is the thing we're going to change. So in the future, the thing I'm going to do now is make this find the nearest 2 bins, and then basically weight how much each bin gets based on distance. So let's see. Right, so I think I did this using difference, which is, it seemed overkill at the time, but now it's actually a good thing because I just sort the differences. Right, I take the minimum here, right, and that's the best difference, and that's the bin I go to. I think target index, right? Yeah, that's how. So instead, what I could do is I could just sort the differences and then take the first 2, the smallest 2, and then now I've already got the 2 closest bins and go from there. So let's do that. Okay, so here's the differences. I'm taking the minimum here. So what I could do instead is do target indexes. Or, you know, let's generalize this. So instead of just having 1 or however many, I'm going to just pick the best couple, and then let's see. I also need a way to assign based on difference. I think it's doable this way. So so instead of just numpy argmin, we're going to do sort. So that's going to sort everything. The ratios are less than 1. So 1 minus the ratio means the closer it is to 1, the closer it is to 1, the smaller it's going to be, the closer to 0 it is. So sort should return everything from smallest to largest. Yeah, order. I'm pretty sure it returns from sort of smallest to loudest. Smallest to largest. Yeah. So that's that. And instead of argmin, we're just going to take this. Oops. And take like the first 2 elements. So that's the smallest 2 indexes. And then the best difference is no longer going to be the minimum of this. Instead, we're just going to take this. Actually, I'm just gonna do this. Diff equals this. Okay, so best diff is now just going to be the best indexes of diff. So the way this works is difference is some array that can be indexed using the values from best index, I believe. I'm just thinking. That works, I think. So I'm just making sure I've got the correct shapes to each of these arrays. Because diff is frequency bins divided by this. Frequency bins should be a one-dimensional array. So everything here should be one-dimensional, so including the index. Right, so this best diff should be 2 numbers, just like how best index is 2 numbers. because we are indexing by these indices. So when you have two indices, NumPy automatically gives you those two out of this array. Okay, so once you have that, I think I can just right, I forgot about one thing, which is I do this for every single bin though. So this is actually not one-dimensional. This is two-dimensional. Yes, I remember now, because I reshape it here. And when I divide, it becomes n bins by n bins. So this is n by n. This is still n by n. When you sort it, it becomes, and then you take the first two, it becomes like 2 by n. Where sorting by x is 0, that means the first dimension, this dimension, is sorted. So then we can take the smallest, and then, let's see, best if we take that. I'm just thinking, does this return? Yeah, there's a bit of an issue here, which is this is going to be 2 by n. And when I index this, Okay, change of plans. Instead of making this general, I'm just gonna take the top two from here. So if I just do this, that kind of solves the problem. So the issue I had was indexing into this was going to get hairy. So instead, now this is one-dimensional for sure, because I'm only taking the first row here and the second row here. Right. So now if I take this and I grab the top index, or I could just do this. Actually, I kind of like this instead. Okay. Yeah, I think that's easier. So now I can just do this, this. Actually, it's just, wait. Oh, I know what I need. I need argsort, right? Because I forgot. Argsort gives you the, yes, argsort gives you the indices. That's what I really need here, right? Yes, okay. So instead of worrying about indices, I'm just going to use sort and argsort separately. So yes, it's not very computationally efficient, but it is programmer time efficient. Yeah, so we'll do this. Okay, so now these are ordered in by size, basically. So like if I took the first element of this, that would be the best index. And if I take this, that the first element would be the lowest difference. And what we had before was just some checking code, and now I can just do this. Okay. Now remove index. So this was to get rid of some bins that are quite far away. I'm tempted instead to have an extra bin at the very top and an extra bin at the very bottom. Kind of sandwich the existing bins between these, and that way any of the things that are out of bounds will naturally kind of have all their weight attached to those bins instead. And then we can just get rid of those bins. Okay. Then what? then I just go through every slice and I'm just copying everything. Yeah, this is a lot of work. I wonder if it's time to rewrite this. Because the quick and dirty way to do this is, like I said, just to clip all the samples I need. I still want to write this though. I think it's important, for sure. You know what? Maybe I'll take a quick break from this. Since it's kind of hairy, the solution is to run away, and instead I will quickly code up the other thing I need, which is combining notes into chords. So that should be really simple. Basically, if we do combining chords, so it should be very simple. Let's say you've got two notes like this. I'm just gonna copy this. Okay, so you're gonna have to imagine that these are like frequency profiles. So the first note has a frequency profile like this, and let's say the second one has one like this. Okay, so the idea is that if you need to combine them together, it should be pretty straightforward. You just add them up. So wherever you have overlap, you're just gonna take the sum of the energy at that frequency. So what you end up with is something like this. If I draw it out, it's gonna follow this curve first, right? And then here, here, because this other curve has more energy, it's gonna add up both of those together. So what you end up with is something that looks vaguely like this. It's gonna like level off here, and then really bump up, and then really come down. Yeah, so that's your sum. And it should be really simple to implement because you're just gonna add together the spectrograms. So I didn't think of this last time, which is why I want to do it now, because it should be quite easy. So we're just gonna create this. We're gonna, let's see. I'm just gonna create a new code box, and we'll call this define combine. We'll just call it combine, and we will have, let's say, some spectrograms. And I'm using the star thing just to be able to input arbitrarily many spectrograms. So the idea is this is you can add as many arguments as you want. That gets turned into a list, and then we're just going to add up everything in that list together. So it should be, the spectrograms should be like n by n. And so one dimension is the time, right? And the other dimension is the pitch. And we don't really care which dimension is which in this case, because so long as they're the same size, we should be able to just add them together. And that's the goal here. So just add them. And it should work because even though these are complex numbers, right, the phases will cancel out if they're opposite phases, and if they're not, they should add together. But this is exactly how you expect the audio to work in real life. So yeah, that should just work. We can just add complex numbers. So numpy.add. Now add only works on two things at a time, so we're going to need to go through all the spectrograms. We're going to need to loop through them. Spectrograms. We're going to add spectrogram to the output. And we're going to, before we start, we're going to create the output, and that will just be zeros. So because we want them to be the same shape as the spectrograms, we will take the first spectrogram in spectrograms and just kind of create a copy of it, except all zeros as the output. So that becomes that, and now we need to update the output as we add each one together and then return it. Okay, so that's nice and simple. So now if we go back to our test zone, we loaded up C and C. So let's try combining C and C4 and C6 here together. Those are just two different C's. Combine C4, C6. Okay, and now we can try playing it back. And also plot the spectrogram for this. And I obviously don't need the other stuff. Okay, so let's give that a try. Okay, so this should sound like 2 notes instead of 1. And it does. Okay, that's great. In fact, I wonder what happens if you combine 2 of the same one together. It should make it louder. Not twice as loud, because, you know, these are log scales. Our hearing is a log scale as well, incidentally. But it should be louder than just 1. So I'm just going to compare these. I'll play back the original C, and I'll play back 2 of them stuck together. So that's 1 of them, and here's 2. Doesn't actually sound any louder. Interesting. I thought it would sound louder. That's funny. Let's just combine a few more together. See if that does anything. It might be normalizing the total volume across all of these. So I wonder though, if I combine one of the other notes with this, what happens? So that's the original. I'm not hearing the top one. I wonder if that's because it's getting drowned out, maybe. You know, the solution is I'm going to put in a different note here, like G3. Okay, so here's the trick. Let's try. I'm just experimenting here. So I've got the original note first, then I'm going to combine it with this transposed note just so I can hear something different, not just another C. And then I'm going to combine 3 of these C's with 1 of these G's and see if that changes the relative strength of each note. So let's give it a shot. That's the original. Playback. Oh, I forgot playback, that's why. Okay, that's better. Here's the combined one. Yeah, you can definitely hear the other note. Yeah. Okay, now here's the one where I added 3 C's and just 1 of the other one. You don't hear much of the other one anymore. Okay, what if I add 3 G's? Original. Combined, and a lot more of the G. Yeah, it makes it louder. So yes, I'm guessing it's normalizing the total, like the loudest part. So you can't just make one note louder by spamming it. But the relative strengths of the notes matter. So combining more of the same note will make that one louder relative to the other notes in this. Yeah, so that's good. That's actually better for my purposes because I don't care about the absolute volume of these notes. I do care about how loud they are relative to each other. Okay, so that was easy, and that actually solves one of the big issues I had, which is like basically combining multiple notes into chords. So yeah, that was a lot easier than I thought. So I guess we're back to the transposition train. Let's go back to there. So the combined part just works, and I'm going to just copy it into the transpose section so that they're kind of in the same area. Okay. And now I need to work on this bit. Okay. All right, here goes. I need to think about the engineering of this a bit. So, my suspicion is it might be easier to go the kernel route. So I describe the kernel route like this, right? Where you have some kind of function which kind of tells you how much weight to put on each thing around a given bin. And that's easier because, well, in some ways it's easier. It's easier because you don't have to... Well, the problem with the way I'm doing it right now is that the ends are an issue, where the highest bin doesn't have a neighbor beside it. Right? So if you end up with something that's higher than that highest bin, you're going to be in trouble. Similarly, the lowest bin also doesn't have a neighbor. So a hacky way to do this is you could throw a bin that's higher than all the other bins ever. And you can kind of guarantee this by just making it a ridiculously high frequency. You can do the same thing at the low end. And if you have these two extremes, you'll always guarantee that they are the closest thing to anything that's kind of out of the range of the frequency bins. So you can kind of imagine it this way. My problem is I can't interpolate on one end. Right. Let's say these are my bins again. Okay. And let's say after transposing, this bin ends up way up here. Right. So right now I can't find the nearest two bins because that would be these two, and that would clearly be wrong. Right. So instead, if I just stuck a bin way up here in the stratosphere, right, it doesn't matter where I transpose this to. This one's just way too far high up for it to ever be close. So anytime you have a bin that's out of bounds like this, it's always going to be closest to these two bins, and I can just test for that, and if it is, then I can just not include the frequency here. That's one option. I don't like this because it's very hacky, right? So you'd have to do the same thing for the low end. The other option is to kind of do it in a more algorithmic way, which is where I just sort the bins. That might be the way. If I just figure out where the bin slots and take the closest to. Okay, I like that better. So actually we're going to undo what I was doing earlier to transpose. So I'm just gonna hit the undo button a bunch, because I realize that the way we have it currently, we are getting the closest two bins. It's just we're choosing one of them. Let's see. Yeah, so instead, what I'm going to do is kind of sort this. Okay, I know what I'm doing. So right now we have our frequency bins and we have our transpose frequencies. We could use the numpy find function. I think it's find. No, it's not find. It is it's search sorted. And what it does is it goes and finds where the indexes are in this the original frequency bins, where you would have to insert your new frequencies in order for these bins to remain sorted. And that actually gives us automatically the two neighbors that are closest to that index. So that kind of solves the problem, actually. Now, for this to work, yeah, and the nice thing is if it's out of bounds, you will get either the smallest index possible or the largest one. It'll either be 0 or n, where n is the number of bins, and that makes it easier to figure out which ones are not working and just get rid of them. So I like this approach a lot better. Okay, cool. So numpy search sorted, and basically everything under here is probably going to get modified after a bit, so you can kind of ignore everything down here. So let's see how numpy search sorted works. We have an array which we're searching, which is frequency bins. And then we have the thing where we need to insert, which is our transpose frequencies. Now A or V here should be any array of values. Yes. Okay, cool. So we can just put in transpose frequencies, even though this is like n by n matrix. I think. Let me think. Yeah, so for every single frequency in here, these are both in time and frequency space. Now, but we only care about each value individually. And we're just gonna figure out where each of those individual things fits in here. So the output of this will be another n by n, which will be the indices. Something like that. I'm just gonna make sure I missed nothing. There's also the side. The side just tells you whether you want the index to satisfy this equality or the other one. I don't care, so I'm just going to leave it as is. It just determines which bin you get if you if your transpose frequency is exactly the same as the frequency bin. It tells you which side the target index falls on. But that doesn't matter, because in that case, the difference between the transpose frequency and the bin frequency would be 0. And so you would assign all of the weight to one of these anyway. Okay, cool. So we've got our target. Let's see. Okay. So now we needed the neighbors, right? So first off, I have the remove indices here. So these are the ones where we're not actually using the energy from these because they're out of bounds, right? And now we can have a nicer way to write this, which is basically anywhere the target index is 0, or n, where frequency bins. So we need the n bins here. And I believe this is a two-dimensional thing, right? Let's see. What was it before? Best difference, yes. So we can just do that. Okay. So we've gotten rid of the extremes. We have our targets, and for everything else that's not an extreme, you can basically think you have like, here's your bins. And let's say I've got a frequency that I want to transpose to 1.5, so that's obviously between 1 and 2 here, right? Like this, right? So what we want is basically this search sorted function will tell us it belongs at like if it was like actually I'm gonna change it up like this. So let's say your original bins are 1, 2, 3, and you have a value of 1.5, right? If we had a value of 0.5, that would get an index of 0 because it would fit right here. That's the 0th index. Because this is 1.5, it will fit in the first index here. So if we're counting through this array, this is the 0th position. So a 0 index means it happens, we want to fit it before the 0th position. This would have an index of 1, which means we want to fit it before this current 1 index. So the extra one we want is at 0, which is this index minus 1. Okay, so basically we want I minus 1 and I. I is from 1 to n minus 1 because we got rid of the n1 and the 0 one, right? If I is 0 or n, those are the ones that get removed. So we don't want those at all. Okay. And then what we want to do is pull out the actual frequencies there and compare it with the transposed frequency. Okay, what's the easiest way to do this? I just realized something, which is kind of silly of me, which is I've been doing this whole thing here. Like, okay, this is kind of funny, huh? So the problem I just realized is that this whole time I've been worrying about these bins as a two-dimensional array when I only need a one-dimensional array. The bins always go to the same places, right? It doesn't matter where you are in time. Of course, the energy changes over time for the bins, but it doesn't. What doesn't change is the mapping from the original bins to the transposed bins. So actually, I don't really need all this extra nonsense here. Down here later. Okay, so I'm just going to treat this as a one-dimensional array, which makes it a lot easier to reason about because all these indices will be one-dimensional as well. Okay, that does make things a lot easier. Target. Okay, so yeah, so if I just take target index -1, right, that will be this I-1 index. That will be the before index. And then the one after, the higher neighbor, will be just target index. And what we want to do with these two is basically dig through our frequency bins. Of course, we want to get rid of the one. Yes. Okay, so I still have the issue of that extra bin. So the extreme ends being an issue. So what we could do is just create. Okay, I see what to do. Plus extras. So what I want to do is add in the kind of the endpoints. Is that the best way? Maybe I should work on this logic first and then decide what to do with the endpoints. Okay, so so you have this index. You have a pair of indices. You pull out the frequencies for those two bins. So you have something like freak bins at the target index and also freak bins at the target index -1. Okay. These are the two adjacent ones. And for each of these, we want to know how far off they are from our transposed frequency. So we can do this using this diff calculation here, right? So we can just take these and divide by the transposed frequency, like this. And then you can also, let's see, we want the ratios all to be less than or equal to 1 like this, right? And in fact, because we're doing this twice, once for this target and once for this target, I think I should actually make this a, I could make this a separate operation. Like I could just split this out. So it will take target frequency and target. Or I can just do freak A and freak B. Okay, and so I just want to abstract out what I'm doing here. Freak A divided by freak B. That's your difference. And then we need to make sure the difference is all less than or equal to 1, and then return it. Okay, great. Now, instead of doing all this here, I can just run this function, which has these two frequency bins from your target index, as well as target index -1. Oops. So there's two differences here. There's the higher one and the lower one. Right, so because one bin's on the high side and one bin's on the low side. Okay. Okay. This was the whole idea here. Great. So now that we've got those two differences, we basically need to compare them in order to choose the weights now. So weight, the I guess the mapping. So I still haven't dealt with those the extremes, right? The bins at the very top and the very bottom. So maybe I should remember that, remind myself. We'll say the edge cases. And that's got to happen somewhere earlier. So I'll put it up there. So here, what's the easiest way to do this? Well, if both differences are the same, right, then the weighting should be 50-50. If one of them is 0, then give it all the weight. If high equals low, weight the same. So those are kind of our constraints, right? So let's see. I think it should be a ratio, because otherwise you can't account for the absolute distance. That could vary. So it should be something like high divided by low. Now, of course, that's going to be an issue if low is 0, right? But I think we can work around that. So this gives us the ratio between these two. Now, one way to get around the problem of this being 0 is you could just like give it an epsilon. You could just add a very small number to it. But I want this to be kind of symmetrical, so it doesn't matter which one goes where. Now, oh, actually, I know something, which is that one of these is same. Now that I'm thinking about it, maybe another way to do this is through log space. That would be a lot easier, actually. So what I could do, instead of doing these ratios, is I could take everything to a logarithmic value of frequency. And then all multiplication values are now addition and subtraction. And then I could just do the closest, like by subtracting instead of multiplying or dividing. That might not be a bad idea. Actually, kind of like that. Okay. So what we could do here is, if we take this and take the log, right? So the way logs work, let's see if I can write this out. Oops. So I'm gonna go back to Colab here. So if I do log, so like that. Okay, so right now I need to know x divided by y, which is where x is one note's frequency and y is another note's frequency, right? And if I take the log of this whole thing, I'm gonna use the align environment. Okay. So this is the same as saying, so what I care about is the relative difference, right? I need some function where I can take this, and if they're the same, you return something. If one of them is 0, you return like an extreme value, and if the other is 0, you return a different value. But this is the same as like if I take the log of this, right? Logarithms have the property where you can split them up like this, right? So now let's think about what happens. Let's say And of course we really want the difference between, I see. We want to compare, let's say y is our target, right? Then we want to know how different x is from y. So if y is the same as, if x equals y, right? So they're the same pitch, right? Then what you have is log x over y is the same now as log y over y, which would be log y minus log y, which equals 0, right? Because these two are the same value. Okay, so that's nice. It means that if you transform into log space and you take the difference between x and y, you're going to get 0 if they're the same. The other situation we care about is, well, now consider you have two x's, right? You have log of x1 and log of x2, and we want to kind of figure out which one's closer. And if they're both the same, we want to return the same value. So let's take a look at what happens there. Actually, I'm gonna do this. Yeah. Okay. There, very pretty. Now, if I have log x1 over y, and I'm trying to compare it with like log x2 over y. Actually, I'm taking the ratio right now, right? So currently, this is what I'm really doing. Something like this. Does that work? No, it doesn't. I think this will work. Yes. Okay, so currently this is kind of the situation we have. We have two differences we're considering between two nodes. One is x1 and the other is x2. Both of them are trying to be compared with this reference pitch. Our real goal is the y pitch, right? And now we're taking this ratio because we want to know which node's closer, x1 or x2. Well, if we expand this whole thing out, right, it's going to be log x minus log y for the first one, and then the whole thing's divided by the second one, so that's going to be minus, and then in brackets we have this other expression for x2. So it's the same expression, it's just you're subtracting the whole thing. So if we expand this out, right, negative, so it's minus x2 and then positive for y. The y's cancel out. So you can see that here. Yeah, so you can see the y's cancel out, so we can just delete that. And so this whole thing becomes log of x1 minus log of x2. Hang on, that seems a little fishy, doesn't it? Because it currently doesn't depend on y anymore. Yeah, that's a bit of an issue, isn't it? We need the distance from y. Okay. So if the difference is 0, that's great. And if the difference is non-zero, why does this not work? Yes, I need the absolute, right, I don't care about the direction of this. So that's part of the problem. What I really need is absolute value here. So that it doesn't matter which way the difference goes. It doesn't matter whether x is higher or lower than y. We only care about how far it is from y. Right. So I think that's the part that's missing here. Okay, either way, if we take the absolute value of this first one, we should be able to compare that between an x1 and an x2. So that would be like taking absolute value here and then absolute value here. So you can no longer cancel out the y's. And then this whole thing, we only care about the magnitude again, I think. So let me think. You're going to end up with two numbers that look like this. And if they're 0, that means they're as close as possible. If they're non-zero, you need to know which one's bigger and which one's smaller in order to assign a certain amount of weight to them. So 0 is the best, right? If it's 0, it gets all the weight. And if they both have the same difference, right, you're going to split the weight evenly. So this sounds like a softmax kind of thing. And by softmax, what I mean is you have two weights and they're not normalized. And what you want is basically to make sure that the weights add up to 1. Okay, I think I know what to do. So let's clear this. Oops, where was I? Here. Okay, so I think what I need is this as an absolute value. So this is our idea of the difference between two notes. And then, in order to, okay, we'll call this d of x. So for difference of x from y, right? And now, what we want is something like this. We want to take the, let's say we have d of x1 and d of x2, and we want to turn these into weights, right? So currently, these could be any value. So instead, what we want is for them to add up to 1. So we need this property. And so to do that, you could just divide this whole thing by the sum. So now we're just taking averages, basically. Like this. Okay, so basically on top, now if we just have either of these numbers, then it's pretty clear that adding two of them together will give us 1. And each of these will tell us how much that particular one contributes. Okay, so that's the solution. We're just going to take this, normalize it by the sum of both values. And so the whole thing adds up to 1. And this will be the weight for the first note, and this will be the weight for the second one. So we have W1 equals this, W2 equals that, and 1 equals W1 plus W2. Okay, so that kind of solves our problem. I'll add an end line there. Prettier with these. Okay. Let me think. Is that good? I think that's good. Okay, so back to here. What we want is, first of all, we need log space now. So I'm going to do that here. In fact, the nice thing is all of these are operations we can turn into log space. Currently, this is frequency bins divided by multiple. So instead, what we can say is like log freq equals numpy.log of frequency bins. Now, so long as this is not 0 anywhere, and we've gotten rid of the first bin because it is 0, right? Because of that, all of these will be fine. Because logarithms aren't defined at 0, right? They go to negative infinity at the limit. So instead, we just avoid 0. There should be no zeros left. So we can take the log, and now when we do this, instead of dividing, first of all, the multiple needs to be, so right now it's this, and when we take the log, we can pull out the multiple. We can do that instead. Right, so that would be the same as saying just, sorry, log, right? Because you take the log of the frequency bins. Cool. So now it's log transpose. This is not any different. Okay, now when we do the searching, this part should be the same. So the nice thing about logs is logarithms are they're what you call it, they're always increasing, right? So what that means is that however these bins were ordered before won't change when you take the logarithm, right? Something that's smaller will stay smaller, something that's bigger will stay bigger relative to each other. So that means we can still search through the log frequencies. Nothing changes there. And same with here. The log transposes will fit right in between the log frequencies as before. So this should not change. Okay. I'm just gonna move this down because this is more relevant to that. Okay, now we can talk about that difference. So the difference between our target, our log transpose now, and our log frequency is going to no longer be a ratio because it's in the log space. As we said here, it's going to be this absolute value of the difference. So we're going to take the difference between log frequency and log transpose, and we're also going to need the absolute value. So that's numpy.abs, and the same thing here. Okay, so now that we've got that, we just need the weights, and remember the weights are going to be equal to this. So the sum of the differences dividing each difference. So our normalizing constant is diff high plus diff low. And we'll call this Z, because that's usually what you call the normalizing constant, which is basically the thing that makes this add up to 1. Okay, and now the weights are going to be diff high divided by Z, and same with W low. Okay, great, and this should mean that W high plus W low is equal to 1. And if one of these is 0, it should, sorry, I just realized something. It should be weighted the other way because if one of these is 0, we want all of the weight on that, right? So whichever one's the bigger one should get less of the weight. Oops. How can we fix that? Well, one stupid way to do it is we can just swap them around. Smaller weight. So, because big diff gives small weight. Okay. I think that works. I guess we'll see. Okay, and the important thing is this, right? If these are the same, if these differences are the same, you should have the same weight. And that's true, because if these were the same, Z would just be 2 of that, right? And then each of these would be 1 over 2, which is exactly half. So you'll have split weights. Now, if one of these weight differences is 0, let's say high is 0, right? So that means that the frequency bin that corresponds to this one is exactly the same as our target transpose frequency, and in that case this difference would be 0, right? So 0 divided by Z is always going to be 0, that means that okay, that's a problem. Because in that case, if in that case, the low bin gets a 0 weight, and that means high bin will get all of the weight, which is perfect, right? And same idea, if low is 0 difference, then this one becomes 0. And so all of the weight goes to here, which is assigned to the low bin, right? So that looks correct. And now that we have that, basically the last step is to go through all of this and assign the weights according to these two weights and these indices here. Okay, so these indices specifically. What is all this? I don't think I need this. I think we need this. Okay, so we get rid of the ones we don't care about. I still need to deal with this edge case, but let's see. Time slice transposed. Okay. I see what I'm doing here. So for every individual bin in a given time slice, it's not quite that simple. Because now I have two indices. Right, that's fine. Because I just need both of these. Yes. Search sorted, right. Okay. So I just need both of these. Target index and target index -1. So currently, right, I'm throwing all of the energy into this one, but now we also need to care about index -1 and multiply each one by the weight. So we actually need it this way because this is the low one, and we also need W low, W high. Something like that. Right, oh, I have the wrong names. So, oops. This is W low, this one's W high. And I'm just gonna rename these because it's not very clear what's going on. So we'll just call weight low, weight high, and do the same thing here. Okay. Great. So the only problem we have left is the edge cases. So what that means is we cannot have this target to be 0 or number bins. If that's the case, then basically what we really want is for the weights of those to be just 0. Like, you just don't send that to anyone. Right? The problem here is, of course, this index. If right now the target index could be like 0, which would give you an invalid index here, or it could be n, which would give you an invalid index here. So if it's either of those cases, what we really want to do is reset those both here, here, and also here in the weights. So currently, here's the differences. And you're already going to have an issue plugging in those invalid indices here. So, probably the easiest way to do this. Just keeping an eye on whether anyone's messaging me about questions. Okay, so if we keep track of the indices here that are out of bounds, then we can set them to something benign. Like we could set everything that's 0 to like 1 or something, right? And here, so the differences that come out here will be garbage for those out of bounds ones. That's fine, because at some point we'll get to the weight here. And what we want to do is then set the weight deliberately here. Low and high. So I guess I'll have to write this out twice, right? Oops. Well, so I'm trying to use the 2. So you can in VS Code you can use 2 of these at the same time like this, right? Okay, that's better. Weight low equals. So what we want is like this guy. Actually, I'll just copy it down. What we want is basically anywhere where like the things are invalid, we're just going to set those to 0 so that there's no weight attached to them. So when we get down to here, it doesn't matter what this target index is, because we're just going to add 0 to that, and that won't change the output at all. So that's the idea here. Now, what that means is we need to figure out where these indices are, which we do here. Right? And I don't think we need where for this, because where gives you like indices, but we can just have a Boolean mask here. So basically each of these is a Boolean operation. It applies to every single element in this array, and basically we can keep it that way. So now it's basically just saying yes or no, true or false to every single thing in this array. So it's the same sized array as target index. Out of bounds, we'll call it. Okay, so basically now we just want to reset everything in target index, which is out of bounds, to something that's not out of bounds, like 1. And 1 is not out of bounds because I don't think it's out of bounds because right, because we need to go to -1 here. That's why we can't set it to 0, because -1 would not count here. So if it's 1, we go to the first bin, and this goes to the 0th bin. Right? There has to be at least 2 bins for there to be basically. This works on adjacent bins, right? So if you only have 1 bin, it's not going to work. Okay, cool. So we set this to some garbage value temporarily. So that solves that problem. We'll just call this reset invalid. Right, and then here we just do the same thing, right? We take these out of bounds ones. We set the weights to 0, so they're not affected later. Now I don't care about this anymore. Because we're setting it to 0 here, right, using these weights. Okay, so now when we go through this, so at some of the target indices, they were invalid. Now they are 1, so they will always point to the same bins here. But that's fine, because these weights are now 0 for those. And we had to do it this way because we were calculating the difference across everything here. And so I didn't just want to like index this using the out of bounds. I wanted to do the same operation to everything here. Okay, cool. That should work. Hopefully it does. So this part just does it for every time slice, right? So that's not a big deal. Okay, and did I end up using freq diff ratio? I don't think I did, because I changed it to log space. Okay, cool. One thing I might do is just abstract out this stuff, because it's doing the same thing twice, once to the high ones and once to the low ones. So what I could, oh sorry, but we have the Z, which depends on both. So I think I will leave it as is for now. Oh, I could call it linear interpolation or something. Yeah, I could call this linear interpolation. Yeah, let's sure, let's do that. Honestly, it's going to depend too much on how transpose is written, so I'm going to leave it as is. Okay. Cool. Okay, so there's no syntax errors. That's good. Okay, we're going to try it. So we'll do this. Playback C4 G3 and I want the spectrogram. I think I called this plot spec C4 and G3. Okay. Okay, so where's the error? Out of bounds. Oh, that's because I'm using OR. This is a Python logical operator, but we really want the NumPy one, because the Python one expects a single Boolean, but here we've got a whole array of Booleans. So to do the OR for every single element in the array, we can use the NumPy version. Okay. Hey, I'm surprised it did not crash. Okay, so I guess moment of truth. Let's see if it actually did the thing it's supposed to. Here's the original. Now this should be scaled down. Actually, we can take a look. Is it scaled down? It's scaled up. That's odd. Why is it scaled up? Multiple. Multiple currently is 0.75. Because 0.75 of the frequency would... That's weird. Shouldn't that go down? I guess it should multiply, right? That's why. It's being divided by frequency. It should be multiplication, which is adding in log space. Yeah, let's try that. Okay, so it went down this time. That's good. Because 0.75 of the frequency means it should go down. Okay, now I'm still getting some pretty weird aliasing effects here. Yeah, and it doesn't sound great because of this aliasing here. You can see the big bands. Huh. Huh. Okay, so one thing we could do is take a look at where it's trying to assign weights and see what that looks like. Before I do that, let me try something. I'm going to try transposing up as well. So I'm just going to do this and just see if it's better or worse transposing up instead of down. Okay, here's the original. Here's the transpose down one with all the gaps. The transpose one up. So transposing up also has some gaps, which is a problem. So that's transposing down. And transposing up, which also has this nasty... Now that is a problem. Okay, I'm gonna take a little look at the weights, and if I can't obviously spot what's going on, I'm just gonna hack it and basically let MuseScore generate all the samples I care about, and then just like use some code to extract those samples quickly and neatly. That might be easier than hacking around with this transpose function. So first, I am going to plot these weights. I want to see where things are going, right? So let's do it this way. What do I want to plot? I need to know basically where each, you know what, I'll just do it this way first. I'll just print out a table, and the table is going to have like the original frequency. We'll use log transpose, that's the target. And I'm gonna concatenate them all together, I think. Log transpose, and then the weights. Oh, you know, I wonder if it's the the issue is the these are complex numbers. That could be an issue, right? Taking the exp and log of complex numbers is not exactly what I want. Yeah, but these are just weights. This is just scalar addition and multiplication, so it shouldn't affect it, because this is the only place I'm touching complex numbers. Alright, these are just frequencies. Okay, so let's just print this first and take a look. Oh, oops. NumPy stack takes in an array. Okay. Okay, so it stacked them horizontally. I didn't want that, but that's fine. So the first number here should be original log frequency. Second one's the transpose log frequency. Third one's the weight to the lower number, and the fourth one's the weight to the higher. So some of these will be 0 because they're out of bounds, right? But some of them will not. And so we should expect, for example, here's some weights. Now, do those add up to 1? This is 0.41 and this is 0.58. So yeah, they roughly add up to 1. Same with this. Yep. Okay, so they at least add up to 1. That's good. Now, the question is, which bins are you assigning these to? So here's the original. Here's the transpose. Oh, you know what might help is let's also print out the indices. Yeah, the indices that we are transposing to. Okay, so now here, the third one's the indices. So this is 1. That means first bin. This is going to the second bin, and so forth. Right? And some of these are going to bigger bins. And this is kind of ugly right now because I'm printing a NumPy array. So it might be better if instead of this, we create a pandas data frame. So did I didn't import pandas, so I will. So pandas is the Python data side, Python data science library, and it just lets you view tables like this more neatly. So we can say create a data frame, and the data is going to be basically each of these things. Oops. Target index. I'm just gonna copy this whole thing over and then fix it. So index, that's the bin. So I'll just call it bin. This is W low and W high. Okay, so I can just print this data frame instead, and it'll just organize everything nicely for me. Oh, I don't have pandas installed, of course. I can fix that. Pip install pandas. Now that might take a little time. Actually, no. Didn't take long at all because I've got it cached on my local computer. Right. No, I didn't. Huh. I just had some of the dependencies cached. Okay, cool. So now I should be able to do this. Okay, see, this is a much nicer way to see things. So you can see the frequencies here, the transpose, the bins. So the question is, first of all, are the bins contiguous? As in, like, do they cover every single number here, or are there gaps? Now, based on what I see here, there definitely look like there are gaps. So I'm really curious about this. Let's try printing everything that's unique in the bin. And incidentally, I will turn off this. I don't want to see all these transposes. Okay, so I'm going to print the uniques. How do I get that? Pandas, data frame, unique values in column. Do a quick Google foo for this. You can just run unique. Okay. Yeah, so here's the unique values. I would like to actually print out all of them. So I'm actually going to change this to like... maybe just a list. Just gonna glance through it. I mean, it seems reasonable, right? So let's test two things. First thing to test is if there are any missing values. So what I'm going to do is create another list, which is the same length. And just see if that's the same. So here I've got X in range of this. So I'm going through a list of the numbers from 1 to whatever. And I'm just going to see whether that equals the value in the bin. So I can do this instead. I'm just going to iterate over both. So I'm going to zip together my custom thing with bins and just see how many of those equal. I probably could have just used NumPy to do this. I mean, so far so good, right? Actually, I am going to use NumPy to do this. I need numpy.all because this will again do element-wise equality. And I want to see if they're all the same. And the answer is true. So yes, there are no bins that are missing. So the problem isn't that we're missing a bin somewhere along the line. The problem is we're assigning 0 energy to some of them. Right? So the other thing I'm curious about is how many bins are repeated. To do that, to test that, I can just do print the difference in length between bins, which is the unique values only, and the values in df bin, which is the column of this data frame, which contains this information. Okay. Yeah, so there's quite a bit more actually. There's like 500 repeated bins. That's what this is telling us. Okay. Interesting. Okay, so there's a decent amount of repetition in bins, like multiple bins are mapping to the same place. Now, the real question is what's happening with the weights? So we want to know, where are the weights 0? df w low. When does this equal 0? And similarly high. Now, of course, this is a huge amount of information. So what we really want is to kind of plot out where this is happening. So let's do that. And instead of doing this, I could just plot out the values themselves. And I'll just plot two separate plots, one for low, one for high. Okay, so wow, that's a complete mess. So let's change it up. We'll just say equals to 0 this time. So there's a lot of different values here, and they're just getting all mixed up together. Okay, so I see something problematic already, which is that it looks like the high values are almost always 0 for some reason. That's definitely an issue. The weights for the low ones are varying, but a lot of them are clearly going to 0. Some of them are at 1. In fact, it looks like... yeah, so that's fine. There's a lot of zeros, so I wonder how many there are. So I can just add them up because NumPy will consider, or it's actually, I'll use non-zero. Count non-zero. Yeah, and I'll do that. Okay, so how many are zeros here? Wow, that's a lot of zeros. Most of them, actually. So in this case, it's all of them, and in this case, it's most of them. So this accounts for all these black bars here. Right, clearly, a lot of these energies are being weighted at 0 for some reason. So let's take a look at why that's happening. Let's start with diff high. So we're going to work backwards. We know that these weights come from diff high and diff low. So let's see what's going on there. Yeah, so most of these are zeros. So the problem is coming from here, right? So let's actually print out diff high. Or even plot it. Okay, so this is diff low. Diff high is here. I mean, a lot of them are negative, so I wonder if the issue is that the differences could be negative. No, they're all positive. Right, because this is absolute value. So yeah, they're all positive. Now, some of them will be pretty small. Yeah, and some of them are indeed quite small. And that's fine. That shouldn't be an issue. Okay, I wonder if Z tells us anything. So Z is just the sum of both of these. Huh. Seems like a out of bounds issue. That's what I'm suspecting now. Because I bet if we went to here, you would not have this issue. So if we print out this. If we go numpy.non count 0, I'm sure this would not be an issue. Yeah. Hang on. It is an issue, is it? Huh. So this means this is not 0. Anything that's not 0 is going to be true. So most of these are non-zero. Right? Huh. Okay, that's a little weird. Yeah, most of these are non-zero. That's good. Okay. Well, where is it out of bounds then? Nowhere. It's nowhere out of bounds, huh? I think there's like a grand total of 1 that's out of bounds. Huh. That's a little weird too. Okay, I'm just gonna check this directly. This is getting a little weird. Yeah, so none of them are equal to this. Oh, because I've already changed this, that's why. Right, so we need to go way up here. There's none of them that are out of bounds? Seriously? Okay, that is really weird. I'm gonna print that data frame again and take a look at it. In fact, I'm gonna save it out. To CSV. So this lets me save this out as a file. And the reason why I want to do this is because if you print it out in the notebook, it won't show you everything. And let's see, where am I? Yeah, I'll just save it into the same directory. Okay, we have freaks.csv. So let's take a look at this. We have, first column is nothing, second one's frequency, third one's the transpose frequency. So let's see what happens. Here we're transposing down, so we expect these frequencies to go down, and that's true. This one goes to here. The bin here is 1 though, that's weird. The reason why it's weird is because this should be the first frequency, and this really should slot under it, right? It doesn't make sense that it's slotting above it, because this is lower than this number. Here you see this number is lower than this number, so it makes sense that it's getting slotted into bin 1, because it would be after this number but before this one. Here this one is between this one and this one, so it's bin 2. That makes perfect sense, right? This is bin 1, this is bin 2, this is bin this is actually the same, right? So it's also bin 2. That's fine. And in fact, you can see the weights here are 0 and 1, which means, oh, the high one gets all of the weight. Yeah, that's wrong. And that's definitely wrong. Okay, so I see where the issue could be. It's just sending things to the wrong bin here. Okay. So you can see this one, for example. The bin is 5. So let's see, 1, 2. Yeah, so if this bin was 2, this bin is 2, yeah, so it matches right up here. This bin is 5. That's totally fine. But the weights are the wrong way around, because the weights should be low and then high. Yeah, the weights are low and then high, and right now they're just going to the wrong place. So the diff, I'm gonna include the difference here as well, because that'll tell me if the mix-up is from the difference or the weights. run that. Okay, now we have the differences. So going back to the one that I was just looking at here. Okay, so the differences are, one has a difference of 0.4, the other has a difference of 0. So here's the differences, right? So the low one has a difference of 0.4. So that tells me that it's an indexing issue. If I look at bin 2 here, right, that's 0, 1, 2. And then bin 1 is this one. Okay, so it turns out that thing I said wouldn't matter, search sorted, has this side value, right? Turns out maybe the side does matter, because this is definitely going on the wrong side. So what's happening here is the index we have is 2, so it's looking adjacently at 2 and 1. So here's 1, here's 2, right? The difference between this and 2 is 0, right? So that would be this high difference, right? And the difference between the low one is some value, which is here, right? That's just the subtraction of this and this. Now here, then the weight all goes on high one, which is fine. That's actually correct. Okay, how about for one of these, like this one? This one goes between 3 and 4. Yes. Wait, no it doesn't. 3.69. So it's smaller than here, right? So it actually should go between 2 and 3. Huh. Okay, this seems fishy already. How about 3.18? 3.18 should go between 1 and 2. And currently it's getting an index of 2, which fits it right here. That's good, right? And the differences are 0.11 and 0.28. That's good, because 3.18 is closer to 3.06 than 3.47. And so the weights are more heavily weighted toward the low one than the high one. That's correct, right? This behavior is correct. Now, for some reason, it's getting it totally wrong here. So 3.69 should fit between 3.47 and 3.76. So it's saying, look at index 3, so these two, right? Number 2 and number 3 here. Okay, and it says the difference is 0.22 and 0.06. Yes, because this is closer to that, and it's assigning most of the weight to this one. That's actually correct. Okay, so that's fine. Now, how about here? It's assigning everything to 3.47. That's fine. Okay, how about here? This one's been adjusted. That's why. That's why it has this index of 1. It's a fake index. Actually, it's just got 0 weights all around. Okay, cool. So everything works as expected so far. I'm just really surprised by why it's not working. So I'm just gonna look through this and see if there are any cases. Oops, that's not what I wanted. Did I just close that? So what I was trying to do is activate regular expressions here. So I want to look for this, but only at the end of the sentence. And I believe it's like this. Yes. Okay, and there's only one of them. So that means only one note has been completely canceled out. So if we jump all the way to the end, when we're looking at this transposition, right, everything's been transposed down. So the top bin here should be totally fine, because what's happened is it's been transposed downwards. And so there are plenty of bins for this number to slot between. And in fact, that's exactly what you see. You can see that this bin fits on line 1535, somewhere up here. 1535. Yes, because this is about 9.7, which is this guy. Okay, so that's totally fine. Okay. There's a lot of bins that look like this, and I'm guessing all of those should have frequencies that equal. So let's take a look, for example, at this. Yeah, so you can see that, for example, here, this target frequency is the same as this bin, so it should assign all of its weight to that. Let's check that. So it's going to line 41. Yeah, this is 41. And that is indeed the value. So, yeah, the weight is all on this one. Okay. Yeah, so it works as expected, at least according to this. So I'm a little mystified that it's not working out here. That is weird, because according to this CSV file, this table, all of these are in the right place. All of the weights are correct, but somehow here it's not. Okay, let's take a look at where this is 0. Actually, I wonder. This is a really weird bug, I gotta say. I guess that's usually how bugs go, because they work in, they fail in ways you don't expect, right? Because everything that I expect to be working is working. I'm getting the right linear interpolation, I'm getting the right weights out, I'm mapping things to right bins, but somehow when I actually go to copy out this, it doesn't work. Oh, of course, I'm equaling. Okay, so what we really need to do is add here, and I totally forgot about that. Okay, well, that's rookie mistakes. So what's happening here is I forgot to add in the previous energy because I'm iterating over each thing individually, right? And I need to sum up everything that goes into the same bin. Okay, that was dumb. Well, that was a lot of work to find out. That was obviously wrong, and now I have a completely different error. Okay, what happened here? Did I reset my... I might have reset my notebook here. Let's just try rerunning everything. Okay, apparently I did reset everything. Okay, cool. Hey, that looks way better. Okay. I can't believe I spent that much time debugging something so trivial. But there we go. So we're loading the spectrogram, transposing it to G. And we've plotted both spectrograms, and now there are no gaps. Okay, so it should sound pretty good. Okay, that's the original. Still sounds terrible. Okay, what? I mean, the spectrogram looks perfect. Like, it really does. It looks like a perfect transposition, but for some reason the sound is not very good. Okay, well, let's try the higher one as well, just for comparison. Okay, here's the higher one. I mean, that one doesn't sound terrible. Yeah, it's still very, like, tinny. You know, at this point, I think I should give up and just do it the hacky way, which is I'm going to generate all of the samples I need in MuseScore and then load them in separately. That'll be way easier. Yeah, so here's the high transposition. It might be this weird noise down here. You can see it's kind of this is almost certainly noise, right? All this stuff that's outside of these main frequency bands. Okay. Well, task failed successfully. Let's move on, I guess. So here's the hacking part. We need samples for every note on the piano. And then to simplify life, I'm going to create a Python script that will just chop up the sound from MuseScore into separate things. So let's start by doing that. We need every note on the piano. So I'm going to create it with a big rest in between so that the sound has time to fade. And I'm just going to create one file instead of a billion of them because it's easier that way. So I need 12 notes for the skit. So it's, let's see, like that. Okay. And just keep repeating until I have all the notes I need. And we're out of bars apparently. Okay, that's easy enough to fix. We're just gonna create a lot more. One thing I don't like about MuseScore, incidentally, is it's got the user interface of Finale, which is a proprietary software that does the same thing, but I've never liked it. I've used Sibelius a lot in the past, and what Sibelius has is a lot more keyboard commands, a lot more shortcuts. Now, I don't know if MuseScore has the same shortcuts, but it would let you do things like sharps, you know, using a shortcut. So that's the whole chromatic scale. I don't need the repeat because I'm just going to copy this whole thing out into the other octaves. So, for example, if I just do this, you can see I have another octave, and there are like 7 octaves on the keyboard, so I will keep going. Okay, and I think that's it. Yeah, that's the highest one. So there are no more. Okay, now we just need to do the same thing, but low. So I want them in order, so I'm going to delete everything after that. Oops, how do I delete measures? Edit. Apparently that is not the way. Well, that's fine. I think. Measures. Okay. Insert measures. Control B appends measures. Okay, but how do I get rid of measures? I don't know. So I'm just gonna insert them at, or you know what's smarter? I'll just copy everything over. So I'll just move everything. Say here. It's a little too far. Kind of eyeballing it. 1, 2, 3. Oh, somewhere along the way I screwed it up. What happened? Oh, it failed to copy out. Huh. Okay, that's fine. Just do it again. Okay. Yeah, I have to say, this interface is not as good as Sibelius. I mean, maybe I'm biased because I used it a lot, but... yeah, that's it. This is the last note. Okay. This time, I'm not going to mess around with it too much, since I'm not familiar with this interface. I'm just going to copy this out a bunch again. Because I'm just going to strip out all the zeros afterwards in Python, right? So I don't really care if there's a whole bunch of zeros. Okay, now I'm going to copy out the octave again, which goes to here. Okay, and I'm just going to bring that down. And do it again. So long as they're in order, the Python script will be able to handle it. Right? So we're here now, and I need a few more. Is that the same one? I think I might have overwritten some. Yeah, I did. Oops. So 1, 2. Oops. I'm missing another one here. Yeah, okay. I somehow deleted a note there. Okay, I'm almost done. There should only be like 3 more notes down here. So I will just copy them out by hand. We have 1, 2, 3. And that's B, and this is A. Or sorry, B flat. So 4 more notes. C, B, B flat, or A sharp. That's A. B flat. Yeah, that's B. Okay, perfect. That should be 88 notes. And if we don't end up with 88 notes, I know I screwed up here. So let's save that out. I will just save it temporarily as all the notes. I'll save it here. And I will also need to export the sound. So that's wave audio, because I don't want it compressed at all. Okay. So let's take a look. It's exporting. It's a big file, right? Because wave is completely uncompressed, and most of this file is going to be zeros. Where is it? All the notes.wave. Okay. I'm gonna move it here. Okay, great. So now I should have access to it. If I go back here, I'm just gonna check. I have all the notes.wave. Okay, we're gonna construct a little script to pull that in and copy it out. So let's just create a new window here, a new bit of code. Okay, so basically first we load the audio file, and somewhere in here there's a way to load this. sf.read is the way. And now I'm lost because, all right, I can search for load samples. Right here, script to extract samples in order. Whoa, whoa, whoa. Jumping all over the place. Okay, the file is called all the notes. D type. Should be float 32. So there are actually different bit rates for this data, but I assume it's float 32. So I'm just gonna print this to double check. should be something ridiculously large, which it is, and I don't care about one of the channels, so I'm going to get rid of one of the channels. Like that. So that gives me the first channel. Yep. Okay, great. The other thing I could do is I could just average over both channels, right? I could do like mean data axis equals 1. That would also work. Yep. Okay, great. So we have this data. Now we're going to basically find all the zeros. And where it's like 0 for a long enough time. And probably the easiest way to do this is with a running mean, I think. So it's going to be a pretty simple and hacky script, but I know it works because I've done it before. The reason why I want a running mean is because this thing is huge, right? And if you handle it like a NumPy array, you could end up using quite a lot of memory really fast. So instead of doing that, I'm just going to kind of run it through one sample at a time and generate my mean that way. So I'll create a buffer which just stores some number of samples. And basically it's gonna go like this for sample in data. You're gonna add it to the sample. And then you're gonna, if the buffer is a certain length, which I'll say is, let's say 100. So it's going to look at 100 samples at a time. I'm going to dump out the earliest number in the buffer. And it should return the 0, the first thing, because buffer.append will stick it at the end. Buffer.pop will pull it from the beginning, right? Okay, so once we have that, we just need the average. Now for the running average, I'm going to do a trick where we're gonna take running sum will be equal to itself plus the sample. And then, of course, we need the running sum to start, which will be at 0, right? And then, right, and I actually want the absolute magnitude because the sample can be negative, I believe, right? Because the waveform goes both up and down, right? So we only care about its deviation from 0. So we just take the absolute value. And similarly, if the length has exceeded this, we need to subtract the earliest sample. Like that. Okay, great. And the last thing is, of course, to calculate the mean, which is just the running sum divided by the length of the buffer. Okay. That's it. So basically, the idea is if this mean value drops below a certain point, we're just going to cut out all that audio. And that's it. So if mean val is less than, let's say, a threshold, where we're going to decide what threshold is, but I'll say it's like 0.001 or something, then we will basically consider this area a clip region. So, how to clip it? Well, what we could do is have a little flip, a switch, which basically tells us whether we are saving this region or not, right? And so as we're going through this, we're going to flip save region between false and true, depending on this threshold and this mean value. And if it's true, then we're going to basically write down a clip that we're going to save based on the index that we are in. Like in this data, we're going through it, right? So we actually need the index of where we are. right? If your mean value is less than some threshold, we need to flip save region to false. But only if it's currently true. And so we also need to kind of write and otherwise, if the mean is greater than the threshold and we're not currently saving the region, we need to write the start of a clip. That's the basic idea. Okay, so what is a start and the end of a clip? Well, we need another thing to save this. We'll call this tracks. Okay. So tracks. And we'll make it a tuple. So start end. And start will be, actually the end will be our current sample, right? And then here we also need to do, we just need to set start. Sorry. So we need start 0. Okay. And one more thing, if the first region is below this threshold, I don't want to record an empty, like a totally empty track here, right? That would be silly. So I could just check for that. I could check if the start's 0 and just ignore that. Well, currently save region is false though, so it's not going to start a track until this threshold breaks. When it sees this, right? This will hit and then it'll set start. So I think that's fine. I do need else though, I think, because here save region is going to be set to 0. Sorry, save region goes to false. That's actually fine because these two conditions will never fire at the same time, right? It will take at least one iteration for one of these thresholds to work. So, and then the last thing to do is we're just going to return the tracks, and I'm going to make this whole thing a function. So let's do that. So we need some kind of data. We need our buffer size. We need our threshold. I'll use scientific notation just because it's easier. Okay, and these things I need as instance variables. Same with the buffer. These are arguments. Those tell us what to do with it. We'll call this def stereo to mono. I might have done this earlier, but I'll do it again. I wonder if we did mono somewhere. Yes, I did already. Okay, so actually I'm gonna change this so that it's like it's an averaging operation. Okay. So I don't need the other one anymore. I can just call stereo. Okay. Cool. So the last thing we need to do is actually just run this clip by threshold of the data. Okay. And of course, the important thing is the length. How many tracks do we get? Ideally, it should be 88 because there should be 88 notes on the piano. Oh, and I forgot a colon. Okay, let's give it a shot. And while I'm doing this, let's see. Oh, hi, Mayank. Hello. Do you have a question? Or are you just hanging out? So, Currently, I'm just waiting for this to run. The good news is it did not crash. Bad news it generated a crap ton of output. Wow. What's up with that? 5,604. Okay, that's not great. So let's see. What am I trying to do? I generated a really huge audio file of samples, and I'm just trying to pull out the samples that I want. So it might be that this threshold is too small. So I need to see if this is working first off. Yeah, so you can see how long this takes to run. This file has, let's see, all the notes is 150 megabytes. And that's because the length of this thing, if I take a look at it, is 15 minutes. So each sample takes a while because I have a big rest in between each sound sample. And so because this is a WAV file, it's recording like 44,000 hertz. So that's like 44,000 samples per second, and it's got 15 minutes worth of samples. Yeah, so I think the issue is that the threshold is probably too aggressive. I'm just gonna set something crazy. Actually, you know what? Before I do anything, let's actually take a look at the data. So one thing I should have done is check what this data looks like. So let's just print out some statistics. I want to know like the min, the max, and the mean. Now, of course, I'm pretty sure audio goes negative and positive. So we need the same thing, but with absolute values. So I'm just gonna do it this way. Like this. Okay. And I don't want this anymore. Okay, so it's telling me the min is almost -1 and the max is about 0.8. Oh, I've got someone else dropping in. Ayush, hi. Please check Slack. Okay. I haven't gotten anything on Slack yet, so that's why I haven't been checking. Oh, I just got something. Okay. So I got a question. Okay, so give me a moment to solve this question. I'll be right back. Okay, questions answered. So if Mayank or Ayush, if either of you are listening in, check Slack. I should have put in some stuff. Good luck with that. Okay. So jumping back here, I was just trying to calculate some stats on this audio file. So I've got, let's see, minimum, maximum, average. Okay, and here's the minimum, maximum, average for absolute values. So you can see there are definitely a lot of zeros. Actually, I probably need a longer buffer. That might be why. Actually, maybe even a more aggressive threshold. Like something like that. So what I don't want is, let me think, buffer. If the buffer is 44,000, it means there's been a second of silence, right? I need an appreciable second, like fraction of a second of silence, because I've got whole rests, really long multiple rests here, and that's what I'm trying to use to chop up my clip. So maybe it's better if I make this buffer size quite a bit bigger. Like 20,000. 20,000 would give you like half a second of grace time, right? And basically, the other thing I could do is make the threshold trigger a lot sooner. So if I have really aggressive threshold, it will only set a silence when this is when it's mostly silent, right? That might work better. Let's see, because the average volume is 0.01. Yeah, so I think I might have had too high of a threshold. And having a bigger buffer, maybe not quite 20,000, that's quite a bit. This is a quarter second if I'd use 10,000. And if the threshold exceeds this, I might need to clip it a little earlier, because if the mean's already exceeding this, the problem is the starts happen very suddenly, right? So it might be better to set the starts based on like a few samples exceeding this value, right? So instead of the mean value, it could just be the sample that we're on currently. Although I really should be dealing this by tweaking the buffer size. So maybe if I just reduce the buffer size a bit and make the threshold really low, that might work. So we'll try that, although I need to change this. Okay. So that'll take probably like 10 seconds to run. Python's not exactly known for its single-threaded, loop performance. This kind of stuff you generally want to do in C. Okay, I gotta reply to something else. So while this is running, I'll look at some answers and questions. Oh, it finished running. Hey, and we have 88. Okay, that's good. That's exactly the number of keys on a piano. Now, I'm not quite finishing answering this question, so give me like... maybe I'll run something else that's costly, and then while we're waiting on that, I'm gonna clip out some tracks and plot them, and that'll take some time to run, and then that way I can finish answering this question. So first, clipping and plotting, we have each track has a pair of numbers, right? Start and end. In fact, if I print it out, I bet that's what you'll see. So let's create a new code block so I don't overwrite what I just did. Yeah, so you can see, yeah, so here's the start, here's the end. So what we want to do is basically go data start end, and that's the clip for start end in tracks. And we'll create a new thing called notes. And basically, actually, I'm gonna do it in one line using Python list comprehension. Yeah, list comprehension. Like that. Okay. Okay, so those should be all the notes, and then I'm going to plot a couple of them. So how do I do that? I want to look at the spectrogram. Now, right now, this is taking... yeah, this is taking in stuff from a file. I don't want that. Plot spec requires a spectrogram, so I need to convert this thing into a spectrogram first. So I need to run this, basically. And now, that's kind of annoying, so instead, what I would like to do... if there's a way to do it, is I'm just gonna create a function to do this. Peaks db to volume qdiff make note mainstream. Apparently I don't have a way, so I'm gonna create a def wave to spec. Where's my STFT function? It's here. I'm just gonna run stereo to mono here again, just in case. And here, you can see right now I'm running STFT in some other places. I'm just gonna see how many total and replace those with what I have now. So let's see where else I do this. There's one more place here. So yeah, that's much cleaner, I think, if we do it that way. Okay, cool. So I need to rerun this. I need to skip, back down to where we were here. Okay, so here's the code that was used to extract the samples. Now I can go wave to spec. Oops. How did I do that? Wave to spec on any note. So I'm just gonna do a couple. Let's like do for you know, I'm just gonna pick a couple random ones. I'll pick the lowest, the highest, and let's pick like some in the middle. 22, 44, 66. So 3 notes in the middle, 1 note on the bottom, 1 note on top. I just want to look at these, right? So spec equals this. I need to plot the spec, and I also want to do playback, so I will also include playback. And I think, does playback work directly on an array? Yes. Okay, so I can just do notes I, like that. Of course, I don't have playback yet. It's down here. So I'm just gonna copy out that function. You can go up here. And just to clean things up, I know it's a complete mess right now because I've got all the imports kind of scattered throughout, but at least I will put them in the same place at the start of that block. Oops, I didn't mean to run that again, but that's fine. Okay, while that's running, I will answer this other question. Something went wrong here. Too many indices for array. Oh, of course. It's not comma, it's 2, like this. Okay. Cool. Okay, this will take an extra minute, so I'm just gonna close this off. Moment of truth. Let's see how these samples turned out. So here's the lowest note, 2 notes in the middle, and then apparently I went out of range for the highest note. Huh. Okay, here's the lowest note. That looks reasonable. That looks reasonable. That looks like a pretty high note. And then 1, 2, 3, 4. I'm missing a 5th note. It's index 87. Oh, this time I only have... Wait a second. That's a little strange. How come I only have 84 tracks this time? I didn't change anything, right? I kept the same buffer size and the same threshold. Huh. That is a little mysterious. Did I change something? I wonder if it's because I changed the buffer size to 5,000. Oops. Okay, one more time. Okay, while we're doing that, I will listen through these. So that's the lowest note. Yeah, that sounds like it. That doesn't... Okay, that's fine. Okay. I wonder how long each note is as well, so I should do that. I should, let's print, so I'm just gonna get the note length. And that's just n minus start for each of these. And we don't need the brackets. Like that. And I'm just curious, how long are each of these notes? My guess is they're going to be pretty similar, but there will be small differences. And so what I want to do is basically clip them all to the same length after. So once we have this, we want something like, take the smallest length over all these, and we're just going to clip all of the starts to the same thing. Okay, this time it gave me 76. What? I didn't change anything here, so it's really weird that it's causing this. I did not change any of these. The data should be the same because it's reading the same file. And somehow it's just giving me like totally different results every time. That is weird. That's really weird. Is there some kind of randomness getting injected somewhere? Oh, there is. Look at these numbers. These are not the same numbers. So somehow I'm getting a different clip this time. That's weird. I'm not saving this anywhere, am I? Yeah, so these numbers should be the same. So somehow they're not. I wonder if it's this conversion here. It really shouldn't be. So I am doing this correctly now. That's fine. Yeah, that's weird. Like my WAV file is actually changing. I don't think I changed it, so it's a little strange. Huh. You know, if in doubt, sometimes what happens is it might be pulling data. Like data might be a saved thing in this. Right. What might be happening is that it really shouldn't be happening, but sometimes you have variables which are stuck in the runtime of this notebook, and so it's kind of screwing things up. So if I restart the kernel, which is just this notebook, and I just rerun everything, it's possible that might solve it. Did I set a buffer size of 10,000 or 5,000 last time? I don't remember. Well, we'll try 5,000 to start. Yeah, wait. Yeah. Wait, what is going on? The mean is really low. I wonder if it is saving somewhere. No, it really shouldn't be. Unless... What's happening in playback? Def playback. No, it just displays the audio. That should be fine. What? Okay, and just in case I accidentally blew up the file, I'm just gonna copy it in again. Just gotta replace it here. And I'm gonna set this back to 10,000 because I know it worked last time. Wait, no, that wasn't the issue. These stats were changed. So it's something about these stats getting changed. I wonder if it's this. So suppose I don't do this, what happens? Of course it's gonna crash. Yeah, so it was a stereo to mono issue. It must be averaging in the wrong direction or something. And if I print data.shape. Okay, I think I know what happened. When we run this, it's taking the mean over axis 1. That should be fine. Although it also gives much lower. Like for some reason this number goes down. Like the averaging process between the stereo channels screws it up. So I wonder if I should just go back to the way I was doing it before. Yeah, that's weird. So before I was before I was taking one channel and that was the sound. And then I tried averaging between the two and that didn't work. Yeah, I'm not sure how you convert between mono and stereo. I suspect, you should be able to just sum them, but if for some reason it wasn't giving me the same result. So whatever, I will just take the first channel of audio and go with that. And then once I have the tracks, hopefully I have 88 of them again for each key. That's good. That's promising. Okay, so now if I do this, there's all my tracks. Here's the lengths, right? So I don't want to print tracks anymore. I know that works. Here's the lengths. Some of them are really short for some reason. Oh, because they're high notes, so they don't ring for as long. So what I want to do then is I want to take end, where end is longer, right? Like some of these notes don't last for very long because they're very high pitched notes. And so to fix that, basically, let's see. I'm curious. How far is each next start from the previous end? So that's easy enough to fix or to check. We will rest lengths. We will do rest lengths where we do start and end so that it's like, let's see. I'm just going to enumerate over track. And then I will do tracks I, and then end is 1, the second number here. Tracks I, start is 0, but here's the difference. This time I want the end from the previous track, -1, and then the current track. So I need to start from 1 here. We'll print it out. Okay, let's give that a try. start on the previous note minus the end of the first note, so it's negative because I should flip those around. But the important thing is I'm looking to see if any of them overlap at all. It looks like some of them do. That's fine. I actually want to print, basically I want to know if there's ever any overlap if I extend this note length thing. So we'll just print both of these values side by side, and I'm looking for places where the notes are long, but the rests are, sorry, the notes are long and the rests are short, right? We want the notes to be either short and the rests long, or the other way around. We don't want both to be long. So let's see. If we have a really short number here, we have a big number here, and should be vice versa. I'm just checking these. So what I might do is I might just clip these to some arbitrary length, because they just look super inconsistent. I just realized the length of rests in between is not consistent either. So to fix that, let's see, what's the shortest note I have? So I'm just gonna check, what's my shortest note here? 5,000 samples, which is about, wow, that's really short. That's like, huh, that's a little weird, because that is really short. Most of these are reasonable lengths, right? 44,000 samples per second. So like having like 100,000 samples is reasonable for a note. Because each note should be like a couple seconds long, right? 44,000 times like 4 seconds would be like 160,000. So yeah, these are reasonable length notes, but some of these have really short lengths. So that's very suspicious. So I actually think some of these notes have been combined together, right? So this is clipping silence or something. Well, it's never easy. Huh. So we might just have to tweak these numbers, right? We might need to reduce the threshold a bit. And maybe the buffer size. Let's try that again. And the other thing we can do here is we can just look through this and see what happened, which was wrong with the notes that are really off. So right now I'm just printing out these random notes I picked, but instead I could pick out all the notes that are really unusually short and figure those out instead. Let's say if the length is less than like 100,000, because that's like 2 seconds or so. 10,000, 100,000. We're going to plot it out and also print out which node it is, which means I need to know what I is. Okay. Okay, there's quite a few notes that are like this. So let's go through them and just take a listen. So this one, yeah, that one definitely is not a note, you can tell. Same with that. Okay, that's a part of a note, which is a little weird because it's really short. Okay. Huh. These are just really short samples. I wonder if it's because did I forget to take the absolute value? Or maybe it's numerical instability. That could also be happening, right? So maybe instead of doing it this way, I need to not use a running sum and just do like a buffer. Or I'll just run numpy.mean of numpy.abs of this buffer. Yeah. So it might be a numerical instability thing because we're adding and subtracting a lot of samples from here. Of course, this will be slow, but that's okay. And this is like a hacky script, right? And it doesn't need to perform well. Now, this threshold also might be not too low because you can hear that there are some silence regions which are being recorded. Of course, the other option is instead of looking at the mean, we could look at the maximum over a region. That might be better actually, because sound is going to fluctuate, right? It's going to jump around 0 a lot. So some of the values will still be 0 or close to 0. But if there is noise, you know, at least some of the values will be far from 0 as well. So that might be something to try here. Anyway, maybe I should think, while I'm waiting for this, let's think about the next step, because right now we've got our notes. We added them to get chords. So the next step is to get the MIDI from our algorithm for proposing a synthesized sound, and basically turn that MIDI into one of these spectrograms, and then compare it with the target spectrogram to see where we're getting things wrong. So the next thing to program is going to be, if I skip all of this, wow, that's a lot of output, so I'm just gonna hide it. Okay, and there's more output. Okay, so the idea is that, let's see, we've got stuff to combine things. That's the important thing. And the transposing part, which we're not going to use. And then the next step is basically we need a new function which takes the combine part and says MIDI to spec. And so we'll have some samples on one side and a MIDI on the other. Something like that. And somewhere in the middle, it's going to call combine on each of the spectrograms here. So each of these samples is going to be a spectrogram. So let's write that down. And so basically, whatever notes are in the MIDI, we need to translate that into basically the index of the spec samples, like this, right? Except here, this will be every single M for M in MIDI, like this. And this whole thing will be an array, which is fine because combine takes in an array. And that's basically how you do it. However, there is this issue. There's also the issue of volume, right? Right now I don't have a good way of controlling volume. So MIDI comes with two things, right? So we need to break this MIDI file into like the pitch, and we also need the volume. And we need to adjust the volume somehow in these spec samples. Okay, I think the easiest way to do it is a weighted sum. So we could just do this. So if the weights are none, we can very simply just set all the weights to like ones. And the number of ones we need is however many spectrograms we have. Spectrograms, weights. Times W in here because I'm adding here. So I'm just gonna scale each spectrogram by this weight, whatever it is, and return that. Okay. So the only thing I need is the weights. Of course, I need to change this now. So now this is a list, and this is also a list because, yeah, now I'm throwing two things into combine, right? So spectrograms and weights. Weights equals some kind of MIDI thing here. This is to do. And then we're gonna combine spectrograms and weights. Okay. And MIDI notes equals MIDI to do here. Wow. Incidentally, the thing I'm running is taking forever. So I think doing this NumPy evaluation is super costly. So I probably shouldn't have done it that way. Wow, okay, I didn't realize it would take so long. 6 minutes, okay, that's too much even for me. So we're gonna need a different approach. I'm just gonna do onset detection, I think. So basically, I'm gonna just look for wherever this threshold exceeds some value and then call it a day. And as for when it goes back to 0, it might be easiest to save the maximum. That might be the trick. Okay, so yeah, that will be much simpler. So the idea is right now I'm taking the average. Average is expensive, right? Especially if you don't do it with the running totals. So instead, what I can do is I can set the threshold as the max threshold instead. So if anything in this buffer is larger than the threshold, I'm gonna flip the switch on whether it's a clip or not. Okay, so that's a lot easier because the way I did it is I bring in, let's see, we'll call this the running max instead. And basically I'm gonna append the sample. If the length is larger than buffer size, I pop this, right? And now basically I'm going to update running max based on what this sample is. Running max equals max of sample and the current running max. Right, so basically if the sample is bigger than the current running max, we're gonna use that as the new running max. Now when it's removing stuff, what you want to do is, if this is also the largest one, this is a little tricky because we don't necessarily want to just remove it. Ooh, we could do a decaying. Oh, so here's another trick. We could do a decaying average. So basically, it naturally decreases over time, and I like that a lot better, because that'll naturally create a kind of a decay. So it's only looking at the most recent numbers. It'll update really fast when you get a loud sound, and then it will take some time to fade below some threshold. So that's actually even smarter. Okay, so maybe I should explain how this works. So the way this works is we're going to have a function that goes like this. Let's say all our samples are over time t, right? Like this. So t is the time of the sample, and x is the sample at that time. So what we want is some average which is sensitive to sudden changes, but also fades slowly, so that we're not cutting off the sound early, right? Because, you know, the sound's gonna fluctuate, it's gonna hit zero sometimes, and we don't want those zeros to basically shut off the sound early. So instead, what you do is something like this. We do x, let's say mu is our mean, right? So the mean at a given time is going to be equal to this, oops. I was trying to use my VS Code shortcuts there. So this guy plus some decaying number, we won't use lambda, we'll just say a times mu previous. So this is a recursive formulation, which makes it fast in our case, because we only care about the previous number we have, and we're going to multiply it by some a, where a is between 0 and 1. So like, let's say, for example, it could be like 0.9 or something, right? So that means that over time, this part is going to decay at a rate of like 10% every iteration, right? So if this is consistently low, like 0, right, this will eventually decay until this thing is below 0. And if this is suddenly really high, like 1, for example, then this whole thing will bump up to 1 real fast. So you can see that this will be very sensitive to sudden changes in x, but not very sensitive to like x being close to 0. It'll take a while for it to fade, and you can control how fast it fades using this guy here, this a here. Right? So that's the idea. Let's try it. What is it? Okay, so we'll call that. So we have kind of two parameters here. One is the threshold at which we say we have a clip. The other is the rate of decay. So we'll call this like let's do 0.99, because that'll be 1% decay every sample. Because you have to remember the samples go by really fast, right? So that's the idea, and we'll call this the mean. It's really not a mean, it's a moving average. Or sorry, it's like a autoregressive term. So we'll call this AR for autoregressive. Okay, and then the other things we still need. So we don't need a buffer anymore. That's the nice thing about it. The decay takes care of that. So basically AR is going to be equal to the previous AR value, right? Because we're basically assigning this new one the previous value, times the decay, and plus the current sample. And of course we need absolute value, because we only care about the magnitude, right? Okay, that should do it. And I don't care about this anymore. So if this AR value is larger than our threshold, then we're going to start a clip, and then if it drops to below our threshold, we're going to stop a clip, right? And this threshold seems reasonable. Now keep in mind, this AR is going to be bigger than the average, right? Because you're adding, like, basically it depends on the size of this, right? But you're basically, if you think about it, for example, if decay was 1, you would be adding whatever the sample is to this total every time. So you would end up with the sum of all the samples together. But this decay makes the old ones fade over time, right? So you basically get a geometric series. Like if AR is constant all the time, like if the samples are all constants, then this is going to be equal to in the limit, like as you keep taking samples, it'll be equal to the sum of the geometric series, which is 1 over 1 minus r in this case. So it's 1 over 1 minus 0.99. 1 over 0.01 is what, like 100, right? So this sum is going to be quite a bit bigger than this threshold. Okay, we'll give that a try. It should be a lot faster than 6 minutes. In fact, you know, a quick way to test this is I'm just going to test it on like a little bit of the data. We'll do like the first like 200,000 samples or so, maybe 500, because like I said, these samples go by really fast. Okay, so that gave me 3 notes, which sounds about right. Let's just try printing all of them. What do we get? Hello? Oh, there we go. Okay. So here's your first 3 notes. What did I print? Note lengths and rest lengths. Okay, that seems reasonable. That does not, and that does not. So for some reason it clipped 2 really short notes. That's a little weird. I'm just gonna print these just to check what's going on here. Ah, no, that's not what I want. I want the starts and ends. Okay. Wait a second. It thinks this is a... Ah, of course, I need to zip these. Okay. Yeah, so this is way too short. And this is way too short. I'm guessing what's happening is when the sound gets kind of low, it gets close to that threshold where some of the samples bump it over this threshold and some of them bounce it below. That's kind of a problem. Let me just double check. Sorry, I've got another message here. Okay. Ooh. Today's been a slow day. Wow. So, let's see. We've got... The problem is that the audio kind of hovers around like some kind of threshold. And then sometimes it dips above that. Sometimes it dips below. And we just don't want that, right? So maybe I still need to take a moving average. The other option is instead of trying to look at every sample, I can just like look every, like average over, let's say 1,000 samples, right? And then just clip based on which nearest 1,000 we're at. That might work. Yeah, because that'll smooth out a lot of these inconsistencies, right? Right now, the clips just kind of happen too soon sometimes. Yeah, so I guess in engineering, like sometimes you have switches that have debouncing. So basically, when you press a switch, it sometimes makes contact more than once. That's kind of what's happening here, right? It's jumping above and below this threshold like multiple times in a very short amount of time. And we just want to get rid of that. We don't want that to basically affect anything. So yeah, the easiest way to do this is just to take coarser samples, right? So as I go through the data, I could just just chunk it up and basically take the average over each chunk and decide whether some chunks are noise or silence, basically. Yeah, I think I might do that because that's a lot simpler. So the way I do this is pretty straightforward. I go, I'm going to split the data by, let's say, so 10,000 is about a quarter of a second, right? So this would be, 1,000 would be a 40th of a second, which is pretty fast. I think I can go a little more generous than that. Maybe like 5,000, right? And then I have my threshold. And in this case, we don't need decay anymore. I'm just gonna take the means of each window. So basically, I'm gonna split up data into the window size. So there should be a NumPy function to do this. Split, yes. Should be along axis. Okay. If the indices is, if there's too much, they will return an empty subarray. Okay, this requires a exact split though, so that's not ideal. I think I need to pad it first. Yes, okay, so I'm gonna pad by length data divide by window size. That'll get me there. I can just do this. Okay, and then I could split that. Chunks. Okay, and I should be able to just compute the mean directly on that. So now I can replace this with the mean, and of course this is no longer what it thinks it is, right? Right now this I right now this I means yeah, this I is the chunk index, and what we want is the actual sample index, so we need to multiply by the window size. Okay. Okay, that should do it. We'll see how that goes. NumPy split. That's not working. Okay, I might need to look up the NumPy split documentation. Okay. 6 by 3. That seems reasonable. That's kind of what I'm doing, right? Oh, I forgot. Of course, window size. That's why. Array split does not... Okay, that's a problem. I thought I took care of that because I'm running NumPy pad, right? So that should add stuff. Okay, I'm just gonna get rid of the extra printing so I can see what's going on here. Okay, so it looks like it padded it to some size. Oh, I see what's missing. I forgot. I need to take the length of the data and subtract all the even divisions out. Okay. And then take this whole thing and subtract that. Is that right? That should be good. Yeah. So this is all the even divisions that you can get in for window size. And then this difference gives me the difference between the actual length of the data and the even divisions. So that'll give you some leftovers. And then I want to add basically enough so that the leftovers plus what I'm adding is going to equal the window size. Yes. Hang on. Now I'm getting a negative value. So this double thing division means like the lowest integer, right? It's integer division. So it should not include a remainder, but I'm just gonna double check this. And I can just double check that. Oops. Okay, so I have okay, that's really weird. Yeah, the data has this much in it. Okay, cool. Oh, that's why. Okay. Interesting. Okay, so I already clipped the data down to 500,000 samples. That explains a lot. Now, when I do that, then the window size is 5,000, so this should equal 0. Ah, okay. Right. So actually, I want the remainder. That's what I want. I forgot about that. Oops. Yeah, that should fix it. Local variable, save regions, reference before assignment. Ah, right. Along the way, I deleted this. Wow, I deleted a lot of stuff. What happened? So I won't need all of those, but I do need some of those. I no longer have a buffer, but I still need tracks. I no longer have the auto-regressive term. I still have this flag, the switch that flips. The start just records where the start of the region I'm saving is, and the pad size is going in here. Here. So I can replace that. Okay, that's better. It's taking a while, actually. And it didn't give me any tracks. Okay, interesting. It might be cutting out the last one, because it never caught this, so I just need a few more samples. Maybe like 10 times that many samples. Now it's taking an alarming amount of time, which means these NumPy operations are not that efficient. So it might be easier not to save out these chunks because it's probably using new memory for these chunks, and this is 150 megabytes of data. So it might be easier if I just enumerate over, instead of enumerating chunks, I'm going to do it this way. Range to length data, right? But we are going to start at 0, go to length data, but we're going to do it in skips of window size. Yeah. Okay, that will work a lot better. Yes. For I in range. Okay. So now we no longer need to multiply by window size. I'm just gonna check if there's any last minute questions because deadline's coming soon. Okay, and let's see, chunks. We no longer need that. We're not padding the data anymore. We still need to run the mean. Actually, can we do this? We'll just do it this way. Data from I to I plus window size. Okay, now of course the only problem is the last one, right? If this is bigger, so what we really want is like the max. The min, whichever is smaller, so that it doesn't go over, right? And I need to subtract 1 because the last index is this -1. Actually, this is exclusive, so it's not going to include that last index, so that's fine. Okay. Oh, right. I haven't actually calculated anything here. So what we want is like numpy mean over that. Okay, great. Now it says there are 110 different tracks. That's a little weird. The threshold might be a little too generous. Oh, right. Of course, we need absolute value. Yeah. Okay, that's more reasonable. And let's take a look at them. So first off, the sizes seem more reasonable. They're kind of similar sizes now. Yeah, and that's a reasonable length. Okay. Yeah, okay, that's promising. Okay. Okay, this is good. It's cutting the notes very neatly. Now there is a little bit of dead space at the beginning, but we can fix that. That's easy enough. I'm just gonna do a more aggressive kind of basically zero cutting, zero thresholding at the start. Yeah, okay, this is good. This is good. So I'm just gonna run it on everything now. $84, and it ran really fast. That's good. Yeah, so sometimes NumPy can be very slow because it's mostly the memory operations, right? Now 84 means we missed some nodes though. That's not great. So what I want to know is basically like the last nodes maybe. So maybe let's take like the last 5 nodes. I wonder if that's the issue here. Okay, that one seems okay. these are bad. So that one is not good. And that one's not good. So there's a couple that were clipped, even though they're probably exceeding the threshold. You know, I'm gonna bring the threshold back down. Okay, 80. So it's cutting out more notes, huh? Well, let's see if at least it's getting the right notes. So we'll see if those artifacts go away. Okay, that part's fine. Okay, that one's still wrong. If I really up the threshold, what happens? Still have 80 notes. I'm still getting this weird. Huh. Okay, well, I guess that's how it is. I mean, I only have 20 minutes left, so I think I'll call it here for today. Pity this didn't work, but it's pretty close to working. It's just like sometimes it's the annoying engineering thing. So maybe what I should have done is just kind of done this in a more hard-coded way. Because what I can do back here is just make this super regular, so it's like every note lasts the exact same amount of time. And then that way, it's much easier. Yeah, so what I could do, for example, first of all, is to make every note like way longer, right? Like this. Oops. Yeah, so that way, it's got lots of time to ring. And then give it like 4 measures of rest. So it's 4 on, 4 off, and then repeat. So let's try that. And this time I'll start from the bottom. 7, 8, 9, 10, 11, 12. And this should be C again. Or A in this case, because I started from the bottom of the piano. The first note on the piano is A. Okay. And then that means I can copy everything out. Yep. Repeat. Okay. Okay, I should do some math this time to make sure I'm doing it right, because this time I'm relying on the timing in MuseScore to get these things correct. So what I need is a calculator. So if you have 88 notes, each note takes 8 measures here. I should have 704 measures. So I'm just going to make sure I have exactly that many. And the measure numbers are here. So 5, 6, 7. Okay, almost there. 706. Oops. So hang on. $706. So previous one 705. This one's 704. So that should be exactly enough. Okay, so let's go back here and copy out the rest of the notes. Okay, for the last bit, I need to change my approach because it's not going to be a full octave here. This is A sharp, B, C, and that's it. Okay, cool. That's exactly right. Yeah, the next one's not a note. Excellent. Okay, so this is exactly 88 notes, and this time they're all the same distance apart, which should allow me to basically chop it using fixed intervals instead of using the fancy stuff I tried. Okay, so let's export this. We'll just export it to the same file, yeah. Sometimes the simplest solutions are easiest, and I forget that. So let's go here. It's gonna take a little bit of time. Okay, and then I'm going to copy that here. Did I copy it correctly? No, I did not. Okay, 1 second. Okay, great. So now that I have that, I should be able to clip by threshold. So I'm not using this anymore. Let's just load it up. And what you want to do here is basically clip it by a fixed size. So I just need to know how long it is until the next note here. I could do some math to do this, or I could just find out where the sound jumps up all of a sudden. So I'm just gonna like do like data. I wonder how long this takes. So if I play from here, 2, 3, 4, 5, 6, 7, 8. It takes about 8 seconds. Maybe I should. Yeah, actually, there's an easy way. I just realized. I know how long this file is, right? And I know how many notes are in it, so I just need length data divided by 88. Okay, there we go. And just to see if this is reasonable, how long is length data? It's like, what, 62 million samples? And if I divide by sample rate, that'll give us how long it takes. $1,400 seconds. Let's compare that to what this says. This says the length is 23 minutes and 28 seconds. Let's just see if that's correct. Yeah, that's 14. Okay, so we're good. This is exactly the right length, and each note should take this long, which if we divide that by the sample rate will tell us how long each sample is. It's 16 seconds. Cool. And that's what I counted, right? So that's correct. So now we just need to actually split the data. So here's where we can use numpy chunk split, sorry. Or you know what, it might be faster to do a loop because this is mostly going to involve memory copying. So for we'll do it this way. We'll go what we want. Okay, so these aren't going to be whole numbers, right? And we will need them to be whole numbers. So that's the start and that's the end. And we're going to take like data start to stop, like that. Okay. Now this is obviously not an integer, so I'm just deciding, do we want the low end or the high end of it? Because the stop will be the low end of this, I think, and this will be the high end of it. I think that's what we'll do. Or I could just be consistent. I just need it to be consistent, so I think I'll just take the floor. So I do need to import math. And then I can do math.floor. Floor function. And same here. Okay. Okay, there we go. That was much simpler. And I don't think we need this anymore. But I'm just gonna go through here and just check that the notes are fine. We'll check the first one, the last one, and some in the middle. Oops, notes high. Okay. Wow, look at those low notes. They just ring forever. I already gave them 16 seconds. Yeah, that one's a little weird. Okay, so the high notes are somehow not working. Interesting. I wonder if the issue is here. It might be clipping something wrong. That's my feeling. That's a little weird. That is certainly a little weird. Like, first of all, why is this only 4 seconds? Yeah, each of these is the same length. That's good. 70,000, 700,000. Do I have the right sample rate? Should be 44,000. Yeah, it is. Yeah, and these are 16 seconds each. So it's a little weird. That when I jump here, I wonder, oh, I see why. Okay, I need to get rid of that. Okay. Yeah, now these are 16 seconds. And if I jump ahead, it fades eventually. Okay. Let's include the spectrograms. No more questions on the course end, that's good. Okay, this is much more promising. So let's listen to these. That's the lowest note. Okay. Some note in the middle. And the highest note. Nice. Okay, that's much more reasonable. Yeah, all of these look quite reasonable. That's good. Oh, this cuts off pretty fast, actually. I wonder if that's because of the... I think it's just the sample. You can tell this sample is kind of short because you can hear the noise and then it just goes away. Yeah, so that's a problem with the synthesizer in MuseScore. Okay, great. So we actually have samples now. awesome. So I'm just going to delete this. I don't need it anymore. I don't need this script anymore. Okay. So here's our samples, right? And I'm just going to make it a function. Okay, great. So that means we can actually generate chords now using this and the combo thing. So I did put that somewhere, the code to do the combinations. Let me see if I can find it again. Here, right? MIDI to spec is what we want. So I'm just gonna bump this up. Let's bring this up above here. Okay, and here, when we're doing this stuff combined, here, we have some spec samples. We need to turn all of these into spectrograms. So let's do that. Wave to spec of a note. So actually what we really want is this. We want to do it here. Okay, next, so here, this guy, get samples, is going to feed into MIDI to spec, right? And here, I just need to pull out two things about the notes in a MIDI file, which are, or a MIDI chord really, which are the pitches and the weights. So for now, instead of actually doing that, I'm just gonna hack it. I will say that the MIDI notes are equal to like, let's say 44, 66, and 88. And then I'm just going to arbitrarily set the weights so that this is like 1, and this is like 2, and this is, let's say the bottom and the top will be loud. We'll make the bottom louder, the middle one the softest, and the top one medium. That seems reasonable. Yeah, let's do that. Okay, so I'm just gonna test it basically by generating some random numbers, and I'm just gonna try running MIDI to spec this guy. And you know what? I kind of feel like I should split this out because this is getting to be a lot of code. So what I could do is I'm just gonna move transpose to its own thing because we're not really using that anymore. Yeah. And that way I can hide it. Okay, and then here I can just run MIDI to spec. I'm gonna get rid of these because the other functions don't have them. MIDI to spec, and MIDI doesn't matter, so because I'm not using it right now. But we do need those samples, so I'm gonna run get samples. Chord equals this. Let's see if that runs. I just created get samples. Okay, there we go. Index error, out of range, okay. Oh, 88 is too high. Of course, that's higher than the highest note. So we'll do like this instead. Okay, so that seemed to work. Now let's take a look at chord and see if it actually sounds like what we think it does. So we need to plot spec and also playback. Okay. Okay, that definitely sounds like a chord. Nice. And that's what the spectrogram looks like. Okay, so this is pretty successful. I will do one other thing, which is I'm just gonna try switching around the weights. Let's do this. Just to see if the weight part works, because that'll be important later for controlling the volumes of things. I don't really hear the top note. But I definitely hear a difference in volume for the bottom and middle, so that's good. Let's try this. If I make the top note really loud, what happens? Yeah, I can hear it now. So it might just be these notes are, that could be an issue. If some of these notes are louder than others after the Fourier transform, that would be an issue, yes. But as a proof of concept, it kind of works. So that's good. And to be fair, we don't need to be super precise with the volume, because that's something that is like not something you can write in a score anyway, right? If you imagine like a pianist trying to play a piece, right? They really only know what the pitches are. They won't know how loud to play each pitch. That's up to the pianist to do correctly, right? So they're gonna rely on their ear and their finger strength to control the voicing of the chord, as we call it. And you don't write that in the music generally, unless there's a really specific thing you want. So I think this is okay, because the important thing is that we can adjust the volumes as we're doing this. Like as we're running the algorithm to match these spectrograms up, we can adjust the volume however we like. So even though they're kind of in the wrong place to start with, you can still kind of bump them up or bump them down until things work. And then once you have that, obviously the pianist will have to work to figure out how to replicate that sound when they're actually playing the piano, but that's okay because that's their job. So yeah, this is good. So next time, what I'm going to do is I'm going to try to run this whole thing on the MIDI files that this algorithm that I have currently generates. And that algorithm, if you recall, I think I might have mentioned it. We have a couple different algorithms that I'd like to try. The brute force one is the one that I downloaded, right? This is someone else's code, and it just matches all the peaks of the spectrogram to notes on the piano. And so I expect that one will have some pretty big errors, and then we'll try some better versions of this algorithm after that. So next time I will get the algorithm running with this spectrogram matching thing, and then we'll go from there. So that is it. The deadline for the problem set has passed, which means it's time for me to log off. And next time will probably be in 2 weeks, not one, and just because things are really picking up here in the semester. There's a lot of grading to do. Anyway, that's it for tonight.